Okay, so good day, everybody, wherever you are in the world, and welcome back to our webinar series. Today, we've got Tom Crowder, who is going to be presenting on the importance of analytics in prioritizing NRW actions, which should be quite interesting. I know Tom's got some case studies from some of the projects he's been working on. So I'll hand it over to Tom, but if anybody has any questions for Tom, you can type them into the chat function, and then I'll ask the questions at the end. Over to you, Tom.
Great. Thank you very much, Gary. Let's check this is working. So this webinar is about the importance of analytics in prioritizing NRW actions. And this is the agenda for today's session. So do a quick introduction, then talk about flows and pressures, leakage calculations, the mass balance. I've got a case study, and then a little bit of a summary at the end, and then some time for questions. And obviously, the whole purpose of this is to share knowledge as part of the water loss specialist group. So just a quick introduction. I don't want to go on too much about myself. So I've been working for Crowder Consulting for 25 years. I've always worked in water networks and water loss management, and I lead a multi-skilled team, and we deliver water loss consultancy projects, leakage detection, and digital services projects. And I'm passionate about training and professional development. And rather than putting a photo of myself, that's a photo of me and my family. It just shows how kind I'm trying to make myself look shorter, so they look bigger by standing on a slope. Little bit of an icebreaker, and this is just really to get you thinking about analytics. Also tries to make me look clever, but not really. So this is called a Gartner hype cycle, and it looks at trends of particular things over time, and you've got different phases of that trends. You've got the technology trigger, peak of inflated expectations, trough of disillusionment, slope of enlightenment, and plateau of productivity. And I somehow stumbled across something in Google, which is where if you put a word into Google, it tells you essentially how much that word has been mentioned in all the kind of publications over time. So put analytics into Google, and then we can see how analytics has been trending over time. So not much going on in the 1800s, but since the 2000s, we can see we've had a bit of a trigger of technology. So obviously analytics has become more important. We had that peak. We had a bit of a trough of disillusionment, perhaps. Then the slope of enlightenment, and perhaps now we're entering into a plateau of productivity where analytics is, becoming more mainstream in everything that we do. So just to move on, first section is about DMA flows and pressures. And really just to go back, to what is a DMA and flow monitoring. And this slide is really just showing what a DMA is. The water network is broken down into small areas known as district metered areas, and the flow is monitored going into and sometimes out of that area. The net flow is the total flow for a DMA, and it's determined by subtracting the sum of the flow of all the outlets from the sum of the flow of all the inlets, which we're seeing here in green. And then the total daily flow is the total net flow of a DMA for one day, and the minimum night flow is the lowest flow in a defined period for a DMA based on the net flow profile. DMAs are sized so that a leak can easily be identified when viewing the flow profile. And a sudden increase in a net night flow is typical of a new leak. So we've got this sudden increase here, and that could tell us that a leak has broken out in the DMA. Again, this is our DMA net flow, our total daily flow, and then our minimum night flow. And I always like the shape of the DMAs, and we say it's a diurnal or predictable flow profile, and it looks a bit like your teeth. So we call it a sawtooth when you go to the dentist and you get an X-ray. When we're thinking about the minimum night flow, for leakage calculations and targeting, this is the most important period for a DMA. And the reason for this is because it's the period of least consumption. And in theory, for a residential area, the only consumption occurring during the night period is due to some people getting up and flushing the toilets, which, yeah, I'm actually finding I'm doing more of. And I do think about that when I go to the toilet in the middle of the night. And the flow measured in this period is called the minimum night flow period, aka also known as a DMA night line. We usually say that the night period is between midnight and 6, albeit several studies show that the hour of least consumption is between 3 and 4. But it obviously depends which country you live in, which region you live in. This is just an example of a fixed night flow period between 3 AM and 3:45 to calculate the minimum night flow for a DMA, which would then be used in the leakage calculation. So we can see the DMA net flow here, and then we're taking an average of the 4 values between 3 AM and 3:45 to come up with a minimum night flow. When we come to understanding DMA flows, we can learn a lot just by visually inspecting them. And when we look at this DMA, we can gain a sense of the quality of data and the level of leakage by looking at it. So we can see that in this DMA, leaks and repairs are changing its profile. So we have some leaks breaking out that are quickly repaired, and we'd refer to them as reactive leaks or reported leaks. And then we have some more long-standing leaks that have caused the DMA to go up, and they've been found over time after investigation. We can also visualize the components of leakage and demand once the attributes of a DMA are better understood. So if we have an understanding about the night use for the households and non-households and the background leakage, we can then understand how much reported burst leakage we've got and how much unreported burst leakage we've got. So it's important that when we're looking at a DMA graph, that we try to visualize that it has several components that it's made up of. When we think about pressure versus flow, then unless a DMA is pressure managed, the pressure profile is inverse to the flow profile, i.e. high pressures occur when flows are low and vice versa. So we can see in this case, the red line represents the pressure, and then the blue is a flow, and we can see that they have an opposite relationship to each other. When a DMA is pressure managed, we can see in this example, the pressure is being lowered at night, and then this will be reflected in the flow profile, which also lowers at night. So just seeing the impact of pressure management on flow. So now to get into a little bit about DMA leakage calculations. So there are 2 methods to calculate water losses in a DMA. There's a night flow water balance method, which is based on the minimum night flow as a starting point, and the daily flow water balance, which is based on the total daily flow as the starting point. So on the left, we've got a diagram just showing the minimum night flow, and then we've got the night use, and we've got our leakage. And then on the right, we've got our total daily flow, which is an average of the net flow, and we've got our consumption and our daily losses. When we think about the DMA leakage calculations, then they will consist of some actual flow measurements and some estimated flow measurements. So some actual flow measurements include continuously logged users and smart meters. And then we're thinking about estimated flows. We're talking about our night use estimates and our daily consumption estimates. And the greater the percent of actual data leads to better accuracy in our DMA leakage calculation. So in other words, the more this green box goes to the right, the more accurate our leakage calculation will be. In a similar sense, when we're thinking about the orange box on the right, the greater that percent is measured, the higher confidence we have. So the more of your flow that is measured will increase your confidence. But that is caveated with that you've got a good night use model and that you've got how frequently you read your meters. Here in the UK, for measured households, for example, we may only read the meters every 6 months. And so when you're trying to work out the flow consumption for a household for an individual day, and you've only got readings every 6 months, it's quite difficult to do. But the more frequent your readings, the more you can predict what your daily consumption is and then what your night use would be. So when we get into the night flow water balance, we use the night flow water balance to calculate leakage in DMAs with a valid minimum night flow and reliable night use allowances. So you've really got to have those two things as a starting point. And when we do the calculation, night leakage is derived by subtracting your actual night flow, so you continuously log night flow, any smart metered night flow, and then your estimated night use, so your household night use, your non-household night use, any miscellaneous night use. And then what you're left with is your night flow leakage, and you multiply that by an hour-to-day factor to give you your daily leakage for a DMA. When we think about the hour-to-day factor and the AZ&P and pressure and leakage, then got a little diagram to illustrate. So imagine this is a topographical diagram of a DMA. We've got our inlet meter, our critical pressure point, our average zone point, and a boundary valve. And we've got our flow measurement and our pressure at our AZP. Well, we know that our leakage will vary throughout the day according to the pressure. And if we're calculating our leakage at night when pressure is high, unless it's pressure managed, we must consider this when converting the night leakage to daily leakage. If we just multiply by 24 hours, we would be assuming that leakage is constant throughout the day. So we have to adjust the leakage by a night-day factor, which uses the ratio between night pressure and average daily pressure to adjust the leakage, which is illustrated here. Now, when it comes to trending leakage, this is showing a night flow trend for a DMA, and we can see the flow rate in litres per second. And we've plotted 52 weeks in this trend. of the night flow for a DMA. And then we can see the different components of the night flow over time. So in the chart, we've got our leakage, which is the biggest bit in this DMA, the red bit. We've got our night use, our continuously logged flow, and then the line along the top is our minimum night flow. And these are weekly trends. And just looking at that trend, because this is the UK and we were talking about the weather before, we always have a cold period in the UK. And you can see how this cold period is influencing the leakage, making it go up. And we also have a warm period, which also bizarrely always makes the leakage go up. And this is, a common argument here. Is it really leakage, or is it demand? And, it is both. I think leakage goes up because of demand and we're not accounting for it properly. But also, when we do have extended periods of hot weather, it does actually cause, more breakouts on our networks as well. So it's just interesting to see those trends of leakage over time. When we look at the daily leakage trend for that same DMA over that same time period, we can see the flow rate in megalitres per day. We've got the trend of leakage. And what is good to do is look at rolling trends where you're not just looking at a fixed value each week, but you're looking back over a longer period to see if your leakage is generally trending up or generally trending down or staying about the right level. And again, we can see that same cold period where leakage jumps up. And usually in the UK, everyone, that's panic. That's when they press the red button. Everyone really gets onto it to resolve the leakage. And then we can see that same, warm period where leakage has gone up too. So they're just some simple trends of leakage that we can do over time. The daily flow water balance can be used to also calculate leakage in DMAs. And what we generally say is you would use a daily flow water balance where you've got an irregular minimum night flow or unreliable night use allowances. And similar to the night flow water balance, you've got your actual daily flows that you're subtracting from your total daily flow. So you're continuously logged and you're smart metered. And then you've also got your estimated daily consumptions. I say estimated, it could be all measured, but on any given day, if you haven't got readings for that particular day, it's always some level of estimation in terms of what the consumption is for any given day. And then the difference we have is daily losses. Now, what we can do with that calculation then is we can compare what we're getting from the daily flow water balance with what we're getting from the night flow water balance. And we can compare those two values of leakage. And this is considered to be good practice because it can help identify potential data issues or integrity concerns within your DMA. And we call this difference a residual difference. It also, if we swap some terminologies around, it also can tell you, how much potential apparent losses you've got. If you're confident in both sets of calculations, one is more equivalent to your non-revenue water and one is more equivalent to your real losses. And it gives you some valuable insight as to the level of real and apparent losses within a DMA. This is another trend, and this is just showing the residual percentage trend. So we're expressing the difference between our daily flow water balance and our night flow water balance as a percentage of total daily flow. And again, we've got a 52-week trend here of the residual percentage for a DMA, and the closer to 0, the better. And what's interesting is you'll never get this, a really flat profile for a DMA. It always will go up and down. That's the cold period. That's the warm period. So we can definitely see an increase in that residual during the warm period, which does indicate that some of our estimates of night use may be too low during the warm period. So that is just another trend that we can do based on these leakage calculations. So next, I'm going to just talk about the DMA mass balance. So when we think about the mass balance, this is where we're putting the net flow alongside the components of demand, including consumption and leakage. And when we're thinking about the residual, here the residual is the difference between the DMA net flow and demand, but we're looking at the residual as a 15-minute profile rather than a daily or weekly trend. And when we're calculating leakage, we're still calculating leakage during the minimum night flow period, but we're adjusting it by the average zone pressure during the day. And this gives us some additional insight about a DMA, and it's where we're starting to use the smart meters to do that. So the building blocks for the mass balance consist of the actual intraday data from smart meters and the aggregated applied unit profiles for each DMA. So in other words, we've got our smart meter data, which we know, and we can use that. But then we use that smart meter data to adjust the data that isn't smart metered to make that data more accurate. And the way that we do that is we generate profiles from the smart meters, and then we apply them to the consumption of each non-smart property. So we're looking at a household as an example. This could be a profile for a particular type of household generated on any given day from the smart meters. And what you'll see is that when you average this profile out, it will equal 1. And then we apply that profile to individual households, to their individual consumptions, and that's how we can then get a profile of what a household that isn't smart metered could look like. And it's the same type of analysis that we do for non-households, where we have a profile for groups of non-households. For example, they could be agriculture, or they could be hospitals, or other groups. The average will always be 1, and then we apply that unit profile to the individual non-households that aren't smart metered to get an idea of what they may be using throughout the day. When we get to leakage, we still calculate leakage in the night period using a similar type of calculation to what I was showing, but we adjust the leakage by the AZP profile. And this is where we use the average leakage and the average pressure at 3 and 4 a.m. multiplied by the average zone pressure at any given time. And this is really just giving you an example of how you do that. And what we end up with then is when we're looking at a single day, the leakage will follow the trend of the pressure. And when we're looking at a 7-day view, we can also see how the leakage trends against the pressure. So it just brings the leakage more to life when we're looking at it for a particular DMA. And this is an example of a DMA with almost full smart meter coverage. So it's got 93.64% smart meter coverage. And what we can see is if we look at this top section here, we can see there's a bit of a gap, and that gap is reflected here in this residual profile. And this shape and this magnitude tells us something a bit more about what might be happening in the DMA. And it indicates that we are missing some consumption potentially in this DMA because it's quite a regular shape and it's usually always positive. So it helps to investigate specific issues within the DMA. And then we can see our leakage there against the pressure, which, is a little bit up and down as well. So it's just to give you a bit of insight about the mass balance and how it can be used in bringing leakage to life, as it were. So next is a case study. And this case study is based upon some work that we were doing with Northumbrian Water in Berwick upon Tweed, which is the northernmost town in England. So you'll see that it's almost in Scotland. So you can see Edinburgh there, and there's Berwick. And just for those football fans there, it's the only English team to play in the Scottish League. So it's very north. And Berwick is an independent water resource zone in Northumbrian Water. And so what that means is this area here that we're looking at doesn't have any links with any other areas. So it's got its own water treatment works that supply it, and it doesn't have any transfers in or transfers out, which some would say that's a good thing, but it's kind of a bad thing because it makes the water resource zone less resilient and more susceptible when there are high levels of demand. Like, for example, when we have a heat wave, and especially that far north, we go we go a bit mad in the UK and start filling things in our garden and doing all kinds of crazy stuff. So we use a lot of water then. And so, although Berwick is quite small, it's rural in nature, it's a high priority area for Northumbrian Water to ensure that the leakage levels are kept low. And the case study that I'm going to look at is just BW11. We did do something in BW42, but I'm going to go more into this DMA called BW11. So, as I mentioned, reducing leakage in the Berwick zone to the target level was a key water resource management objective for Northumbrian Water. And it was successfully achieved in March 2025. And really, so what this trend shows is the leakage for the entire zone in cubic meters per day. And in this case, have trended 104 weeks, which is essentially 2 years, so that you can see how leakage is changing over time. And then you can see in 2024, there was a particular issue with a leakage breakout. And that was, a big headache for Northumbrian Water to solve. Now, BW011 is the largest DMA in Berwick, and it has had the highest level of leakage. And this is just a picture of BW011, and I think anyone can see it looks a bit of a nasty one. It's got some of the town down here, and then these are trunk mains that go through it across the river. So it's got 2 bridges and then goes up to this north area here. So from a leak detection perspective, it's quite difficult to survey. You can see the size of it here, about 1,000 properties, and its mains length, 20 kilometers. Now, reducing leakage in BW011 was critical to meeting the zone's overall leakage target, as it accounted for 32% of total losses. So you can see again the flow rate in cubic meters per day. Again, this is a 2-year, sorry, trend of the daily leakage for BW011. You can see it goes up and down, but then you can see how this leakage here has gone up and not come down again. And this is the problem in Berwick. So that leakage breakout that we saw in Berwick was, what we're looking is the main problem is in this DMA. We need to sort this DMA, and you can see how the leakage then came down. Which is, so what I'm really going to say is how did we get this leakage down? So looking at the flows and pressures for BW011, as I said, it's a bit of a nasty DMA. So it had 1 inlet meter and 6 outlet meters, but its net flow lacked a typical diurnal pattern. So if you look here, we've got the inlet flow here, which is nice. We've got the AZP pressure here, which is doing the opposite of the inlet flow. But when it comes to the net flow, it's a bit up and down, and it doesn't have that nice diurnal pattern that you would expect. So we wanted to, understand that a bit more. And to do so, we installed an ultrasonic meter in line with the inlet meter. And what we found is, while the daily average flow remained largely unchanged, variations were observed at 15-minute intervals, particularly during the period of the night flow period. So you can see here these little spikes during the night. And that's obviously affecting our leakage calculation. But overall, the difference up and down, it wasn't that far off as an average flow, just these individual 15-minute periods. So although the inlet meter had known issues, we still remain confident that the DMA was experiencing a significant volume of leakage based on the historical trends and the daily flow water balance. And we estimated the leakage to be in the region of 7.5 litres per second or 0.65 megalitres per day. As mentioned, the DMA proved challenging to survey, and Northumbrian Water had already employed both conventional and innovative techniques, but hadn't got to the bottom of the leakage. So therefore, in collaboration with Northumbrian Water, we recognise a need for a different approach. So what we devised was to rezone this DMA, BW011. And we were going to feed the north section from another DMA, and then feed the south section too from another DMA, and just leave what we felt were the nasty bits of this DMA, the trunk main system. And that would essentially be about 5 kilometers of mains and 188 properties. So the first bit that I'm going to go through is this bit, this green bit here, which is the rezone of the south section. And when we devised this rezone, we wanted it to be a permanent rezone because we wanted to increase the size of BW006, which was a small DMA, and make the most use of its inlet meter, which looked good and reliable, to feed the area in BW001 that had the most properties, High Cliff. So you can see we want to feed this section here from BW006. We'd also end up feeding another DMA from BW006, and that's what BW006 is currently. And then we devised a series of steps to do that rezone, which was carried out during the night. In terms of BW006, the reason why we picked BW006 was because we felt that this meter wasn't getting the best use anyway. It's only feeding 39 properties, but it's 150 millimeter pipe. And that is the same size pipe as what is feeding BW011. So also, this meter is located very close to the other meter. And, it's quite a simple thing to do to swap them around. So we can see what the flows were there, quite a low flow rate. And then this is what happened after the rezone. So the rezone was successful, and we shifted approximately 1.5 litres per second of leakage from BW011 to BW006. And in BW006, it would be addressed separately because it's a much more typical area that we can find the leaks on. And when we did the rezone, ignore this big jump here because it doesn't take into account the additional outlet meter. So you can see before and then after, and what the net flow looked like before and what the net flow looked like after. And you can see we've still got quite a bit of leakage to go at in this small area, and that can be done separately. Now, when we look at the flow for BW011, it's more difficult to interpret because of this pattern of the net flow. But we still estimated there's approximately 6 litres a second of leakage remaining in the rest of BW11. And so that's just showing you from the BW11 perspective what that rezone looked like. And again, we needed to take into account the removal of the outlet meter. So you almost have to ignore a little bit of the flows here. And we also did a rezone at the same time. So ignore that bit there for now. That's what it looked like after. That's what it looked like before. So we were happy with that. We left it in place, monitored it carefully, and it's all stood up. And it's worth noting that before we did any of this rezone, there's already a model of the network that the network analyst ran, checked everything, made sure it all stood up to scrutiny. And then afterwards, obviously checking the turbidity, checking the pressures, and all stood up nicely. So the next thing that we wanted to do was to do what we're calling the Meadow Hill rezone. And this would be a temporary rezone to increase the size of BW10 and reduce the size of BW11 to see where the leakage is. So the plan was to feed the north section via BW10, and that was a small section here, 162 properties, 4 kilometers remains from there. And that's a trace of this north section. Now, what happened is, just to cut a long story short, there was no leakage in this north section. So then we had to do several iterations of making the area that BW10 fed bigger and bigger and bigger to pinpoint the location of the leakage, which was all in one small area. So what you can see here is where we're doing Meadow Hill rezones, here, here, and here, and then where the leak was repaired. And it's quite difficult to see on this, but you can see the rezones. But when you look at the Meadow Hill DMA, it's a lot clearer to see the impact of the rezone. And we more use this DMA, to assess the level of leakage. And we hit the jackpot around the 21st of February. So in this period here is where you'll see that jump up, which meant that we in these ones, we weren't feeding the leak. Whereas in these ones, we were feeding the leak. And then the last one, we really narrowed it down to a small area. So you can see, that jump up. Now, this wasn't all leakage. We had to take into account that Meadow Hill was feeding an additional outlet meter. So we did that analysis separately. So then this is really just a summary of the iterations that we did to hunt down the leakage. And all the rezones were carried out by Northumbrian Water, their team. They did all the rezones, and because they know the network and they wanted to solve the leakage as well. And so really we did several iterations, but in the first one, it was just the red bit. Then it was the red plus the yellow plus the green. Then it was just the red and the yellow. and that's where we got the first bump up. And then, you know, we narrowed it down to this section here, the red plus the yellow, excluding this circle area. And we knew then that 6.5 litres per second was in this section. And this was the final rezone where we narrowed down the 6.5 litres per second to the small area on the map. And just showing what we did, we had to close 3 valves and resupply it. And we then went out at night. Once we knew it was in this section, we went out at night to correlate it and pinpoint it. And we found the leak, which was a mains burst here on this main road. And it was worth around 5.5 litres per second, as you can see here, once repaired. Now, the orange bit is just saying, well, why couldn't you find that leak in the first place? So it's just really some lessons learned that there's a PRV here, and that does drown out the noise. You know, it impinges you when you're trying to do leak detection. There's a customer side leak here, and that in fact was worth 1 litre per second, and that was fixed the following leak. So again, that can distract you a little bit as well, because you've got a customer side leak there, and it's, you know, a bit of noise. And importantly, there's this valve on the roundabout that wasn't accessible during the day, only at night, because it's one of them roundabouts that's not a roundabout where cars can drive over it. And so, you know, that valve wasn't listened upon or noise logged. And again, that impinges things. So just to get to a summary, the importance of analytics and prioritizing NRW action. So hopefully I've shown why it's important to understand flow and pressure, and how analyzing flow and pressures helps you gain a deeper insight into your DMAs. And then how you can do a water balance assessment using night flow and daily flow analysis to evaluate the overall water balance for a DMA. We've looked at some more advanced analytics where you can leverage smart meter data and the mass balance techniques for more precise analysis. And then we've looked at a case study, you know, where you're combining the data analysis with targeted field investigations to localize leakage within the DMA. That's it, finish. Thank you. Any questions?
Thank you very much, Tom. Very, very interesting. And I suppose there's going to be a lot of utilities that are embarking on their smart metering programs that would find that quite interesting, because they're going to have to start analyzing all of their DMAs in a similar way, I would guess. We've got a few questions that have come in already, but if anyone else has any questions for Tom, you can type them into the chat box, and then hopefully we have time to ask him those questions. So the first question we got is from Kate.
Should I stop sharing now?
No, you can keep it there in case you would need to go back to a slide to show something, maybe. Yeah, Kate asks, in the mass balance, do the unit profiles of consumption for households get adjusted for the number of people in the household?
So we use, it's quite a long-winded answer, sorry, Kate, but they do inadvertently get adjusted, but it's a different method, because what we're trying to do is use the smart meters in the DMA to adjust the profile of the household consumption in that DMA. So we're not touching the consumption. That is already, we're assuming that consumption is we're assuming that consumption is right, and then all we're doing is we're adjusting the consumption of how we profile that throughout the day. So it within the consumption itself, it should already be accounted for if it's got higher or lower occupancy rates. Because the in the model itself, that's what it does. So we don't play around with the model too much. We more adjust what the model is giving us or what the actual consumptions are.
Okay, thank you. We've got one question from Mosen, which is, how can you analyze the minimum night flow when there is water storage tanks in the buildings? And I'm not sure whether this would be continuous supply or maybe intermittent as well. So you've got tanks
Yeah.
filling at night, I guess.
Yeah, I guess if they're on a smart meter or if they're continuously logged, then they would be already um, included in the leakage calculation when you're using the night flow. If they're not smart metered or they're not continuously logged, then it makes it difficult and makes it difficult to use the minimum night flow to calculate your leakage because they're difficult to estimate. And that's kind of where you'd more revert to the daily flow water balance for those particular DMAs if you don't know what they're using at night.
So I guess you'd need to send teams out there to maybe read some of the meters at sort of hourly intervals to try
You
and get
can if it's
night flow.
predicted, yeah, but if it's unpredictable,
Yeah,
it's
yeah.
very difficult to do. So that's why they tend to you'd smart meter those ones first, because then you'll
Mm.
get the actual flow through them, and then you can do you do your water balance.
Yeah. And Mosen has another question, which I think maybe you did answer, but do you think night consumption per person per hour is a constant value for different days of the year and even different days of the week?
What does that mean? I think it changes
Hmm.
for different days of the week and for different days of the year. If that, so I feel like not feel like it varies. Night consumption varies
I
depending
think
on
it
the
would
time of the
do
year
from
and depending,
temperature, and
yeah,
uh, I guess it would change considerably.
yeah. And it's times of the year and also during events as well
Mm.
that it will
Mhm.
change.
Yeah. Okay, we got a question from Alan, which is an interesting one. It's I understand from several specialists in England that Ofwat has initiated a review of bottom up versus top down. I heard there was more interest in top down due to uncertainty in night consumption and increasing use of meters in England. What's your view?
Oh no.
I mean,
I think
if I
off,
just say something here is that
yeah,
Ofwat contacted us, the water loss specialist group, and as a group, a few people made comments, and we did send our thoughts back to them. And I think they are doing a review at the moment of it. And hopefully they'll come back to us again after they've reviewed our comments. But I think top down is possibly the way that they will be moving forward, or a mixture of the two, a bit like what Tom's been talking about today.
I think the confusion is when in the UK when we think about top down and bottom up, what we're thinking about is top down as in doing a water balance for your entire company, and bottom up as in adding up all the leakage from all of your individual DMAs and
Mm.
comparing the two. Whereas I think that when we talk about top down, bottom up at a DMA level, you know, it's basically just doing those two different water balance approaches. And and you're right. There can be a lot of doubt about the night use allowances and night consumption that makes you question the leakage, for DMAs based on the night flow. But yeah, that's kind of where the smart meters and having best estimates come in. So my view is I still think you need to do the night flow analysis for your individual DMAs because that's the best way to work out what your leakage is in an individual DMA. But obviously when it comes to doing it for the entire company, your top down is, is accurate.
Yep, thank you, Tom. Yeah, we got one question from Mohammed Mansour, and he asks, one question, did you have noise issues with the ultrasonic meter?
I don't think we did, but as I didn't install the ultrasonic meter, so I wouldn't know. But um, I'm not I'm not an expert on ultrasonic meters, so I don't know whether we had noise issues or not.
But it did
Um,
seem to give quite a good correlation with the inlet
yeah,
meter. It was just less spiky, wasn't it?
yeah. The inlet meter was the issue, and it was
Mm.
because it was on SCADA, and so we weren't getting proper average readings every 15 minutes. It was more like um, a reading at that time, and that's why we were getting them spikes.
Could you not have put a data logger on and start recording at 15 minutes and as a
I,
sort
I
of
think
dual recording?
I think they can't, like, because it's obviously not our meter, but
Mm.
because it's all set up on SCADA, that's what they'd like to do, but they
Mm.
couldn't do it as, they couldn't do it there and then, if you like. So that's why we installed the ultrasonic, just to check what was going on.
Yeah. Okay. Um, and we've got one last question at the moment from Gerald, which is, I was dealing with 600 DMAs. The chief priority was keeping all consumers continuously supplied. What I normally assume is that the leakage is 50% of the average, or the average less. The minimum night flow is the target minimum night flow, and then compare based on difference from target. We had some DMAs with full smart meter penetration, but many registered zero flows, and it was a waste of money. I don't know if you have any comments on that. It's quite a long, it's not really a
Oh no,
question.
Gerald.
It's
Yeah,
almost more of a statement of
yeah,
using
because
smart meters to analyze things.
yeah, because Gerald, I think it was County Cork that Gerald, and they had the smart meters, and um, yeah. So I think he's just sharing what they did, there.
Mm, yeah, yeah. I mean, do you think that when, because I know that most of the UK utilities are moving quite fast to almost 100% penetration of smart meters. And I think it was Uckware produced a report where they were saying that it wasn't going to be easy to actually do this sort of analysis with all of this smart data that's coming in. So I'm just wondering whether you think it is going to help, or it's just going to make it, there's going to be almost more analytics and more time wasting.
Well, I'm obviously going to say it's going to help, but it is more analytics. But you're getting we've got the power of computers now that can do that analytics for you, and then
Mm,
you get presented with the results. And once you start looking at the mass balance for each DMA, every single person gets hooked on it because it shows you, different a different insight to your DMA, can confirm, the leakage that you're looking for, or can tell you other things. So yeah, it is a lot more analytics, and it's going to cause, what's the right way to say it, more work.
mm.
But then I think over time that it will become like best practice, if you like. It will become more normalized, and you get to the point where it becomes like standard.
Yeah, we've been talking about it for the last 5+ years. Is this big data? How do you manage that big data in terms of the amount of information you're getting without being paralyzed by it?
Yeah. I mean, the way we handle it is it's on the cloud, so that it's doing all the analytics on the cloud. And then obviously that requires a lot of computer power, but it
Hmm.
can handle it now.
Yeah.
It's got, you know,
I mean,
it can handle it.
yeah, Gerald's put down a couple more comments. I can send them to you, Tom, but it might be worth you discussing further with Gerald offline about how is the best way for him to be managing his data.
Yeah.
And we've had one more question from Katarina, which is how many days per week, for example, of available metadata do you usually need to deem the data available, usable for analysis?
We usually say 3 days in a week. If it's got 3 days in a week, then we deem that week to be available and good for analysis. That's what we do in the UK anyway. You know, that's the measure we say. If it's got 3 days in a week that are good, valid, that means that week is available.
Yeah.
Or more than 3 days in a week. Yeah, more than 3 days in a week.
Okay, that's great. Okay, that's the end of the questions, Tom. So I'll send you the document, Alan, and I'll send you the questions, Tom, with Gerald's contact so that you can discuss further, hopefully after this. But thank you very much, and we will see everybody at the next webinar, which will be coming up in a couple of weeks' time, I believe.
Thanks, Tom. Thanks,
Okay,
Gary.
thank you. Thanks.